Intro to Electrodynamics. This is a trick problem. And I'm going to do it the non-trick way first, and then we'll do it the trick way. I don't really like the trick way, but let's just get to the problem. The problem says, it's problem 2.10 out of Griffiths 4th edition. It says that you have this cube, and it doesn't even say the size of the cube, which doesn't actually matter. But we have some cube, we'll say it's L by L by L, and we have a charge Q at the origin. And the question is to find the flux through this one panel on the side of that cube. Okay, to kind of see the picture, is my picture okay? So let's just say that this is the, let's say this is in the y direction. So this is L by L by L, okay, and that's a charge Q. So first of all, we're going to start off with Gauss's law. No, we're not. We're going to start off with flux, right? So we define flux, not Gauss's law, but the flux as the integral of E dot n hat dA. So this is not Gauss's law because it's not a closed surface. That's part of the hint later. But let's do this the right way first. So if I'm over here, I'm going to draw a side picture. So here's my area right here. This is the z direction. This is the y direction. And there's a little piece of the block of that wall right there. I can break it into little pieces that have an area dA of dx dz. And so that piece, I can find its location. It's going to have an electric field in this direction like that. And then n hat is going to be in the y direction. Right? So n hat is equal to the vector 0, 1, 0. It doesn't change. As I move over the surface of that, n hat is always the same. dA is equal to, like I said, I drew it right there. But I need to find an expression for E. So we're going to do what we've done the whole time, I've done, and that's to follow the following recipe. So first I'm going to write RQ, the vector location of the charge. It's at the origin. Okay, so that's not that hard. Now, what's the vector location of a point up here? I'm going to call that my observation location. There's a whole bunch, but I'm just going to call it generically. So let's say generically it has some x component, which we don't know. It has a y component, which is L, right? They all have the same y value, and then it has a z component, z. So we don't really know exactly what it is. But I can find r, the vector from here to there. It's just going to be RO minus RQ, and that's going to be just x, L, z. Now I can find the electric field due to each one of those, at each one of those observation locations. So E is going to be 1 over 4 pi epsilon naught Q over the magnitude of r squared, r hat. Now I would have to find r magnitude. R hat I don't have to find, so I can write this as 1 over 4 pi epsilon naught Q over the magnitude of r cubed vector r. Right, because r over r magnitude is r hat, and then I just get r cubed there. So let's go ahead and write down the magnitude of r. That's pretty easy. It's just going to be equal to the square root of x squared plus L squared plus z squared. So now I can write my electric field. E is 1 over 4 pi epsilon naught Q over that x squared plus L squared plus z squared to the 3/2 times the vector x, L, z. Right, so this is that. I have that component up there too. Okay, so now we can start erasing some stuff. Let's go ahead and write this integral. Phi is the integral, I'll make it a double in just a second, of E dot n hat, but that means that we have this dot that. So I get 0 x component plus 1 times the y component plus 0 times the z component. So I only get 1 over 4 pi epsilon naught Q over x squared plus L squared plus z squared to the 3/2 times L. And then I have to multiply by dA, which is dx dz. And then I need to find the total area. I'm going to need to do a double integral. So I'm going to go from x is 0 to L, and then I need to do z is 0 to L. And that is what I need to evaluate to find the flux. It turns out, I think, I'm not 100% sure, I think one of these integrals isn't too bad. You can look up x squared plus a squared to the 3/2 dx, and there is an answer for that. But when you do that, the next integral becomes super, super bad. Super bad. Okay, so what I'm going to do is to do this numerically, because I thought that'd be fun. So numerically, what I'm going to do is just vary my values. I'm going to say dx is 0.01, dz is 0.01, L is 1, and then I need to pick values for this other stuff. Let's say Q is 1, and then let's say epsilon naught is 1. Just for now, just to make it easier. In some units, it's true. Okay. So then what I can do is to calculate the area element at each different value of x, and then for all those, add them up for each value of y. I'm really going to be doing this in the xz plane. I'm going to just take box, 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 add, 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 add. That's what I'm going to do. Okay, but I'm going to do it in Python. So this is a great chance to practice our numerical integrals in Python. So I need all these values, and then I'm just going to add up from over the x and then add up over the z's. It's going to be a double loop. Jump into Python. We're going to do it in Python. And then I'll show you the trick. Don't worry. If you're here just for the trick will be coming. Don't worry about that. Okay, so let's put in our values. L equals 1. Ooh, that's weird. Q equals 1. Epsilon naught EP is 1. Dx is equal to 0.01. Dz is equal to 0.01. That was it. That's all I needed. Okay. Oh, and now I'm going to say phi. Phi is my flux. It's 0. Because I'm going to calculate d phi in each loop, and then I need to add it to the total. So I need a total to add it to. So let's do while z is less than L, x equals 0, while x is less than L. So that's my double loop right there. Be careful, be very, very careful that you do not get stuck in an infinite loop. Happens to me all the time, and it's awkward. So let's just go ahead and calculate d phi. So I'm going to call this d phi. It's the flux over that one little bitty area. It's equal to, now I have this whole thing to type in. I'm going to put 1 divided by, I'm going to put this 4 times pi times eps. That's that constant right there. And then I guess I'm going to pull the QL in there too. Let's put the QL up here too. Q times L. They're both 1. It doesn't really matter. Okay. Now I have, I guess I can put the dx and the dz up there too, but let's just say times dx times dz divided by x squared plus y plus L squared plus, oh, you know what, you can't even see. My mistake. Okay, L squared plus z squared raised to the 3/2. And then once I calculate that, and you can't even see that thing either, because I messed up, I'm a bad person. I don't know why this is off. No, it's too small. Okay, that's fine. You just have to deal with it. So now I can say phi is equal to phi, spell it right, plus d phi. Now, nope. Now I can move my x over. So x is equal to x plus dx. And then I'm going to repeat, once I get up to L, I'm going to move up one level of z and repeat the whole thing. So then once I get done with this, I'm going to increase my z. Z is equal to z plus dz. But every time I go back to the x, I have to go back to the beginning. And that's it. Print flux. Oops. Let's say phi equals phi. Let's see if it works. Nope. Line 10. Oh, I didn't put x equals 0, z equals 0. 0.042. Okay, so now let's just check. We'll do this another way, and then we'll come back and we'll check and see if we get the same thing. Okay. I do want to show you this. What if I change L to 2? It's the same value. So if you move your box, make your box bigger further away, you have a larger area. The area is going to get bigger, but the electric field is going to get smaller by the same amount. Okay, let's do this the trick way. Tricks are for kids, but whatever. Okay. Imagine that I have a charge at the origin right there, Q, but I break this into a box like that, and each of these boxes is split into 4. If I do that, this box right here, that face is my area right there, okay? So, but this is a closed area, so I can use Gauss's law. E dot n hat dA is the flux, the total flux, and that's going to be equal to Q over epsilon naught. Well, I only care about the flux, so it's just going to be Q over epsilon naught for the whole thing. But every square should be the same due to symmetry. So here I have number of squares is going to be equal to 4 times 4. Is that right? 4 times 4? Let's see, wait. There's 1, 2, 3, 4, and then there's 6. There's 6 faces to a cube. So that's going to be 24. So the flux for one cube, we'll call that flux 1, is going to be the total flux divided by 24. And so the total flux is just the charge inside, Q over epsilon naught. So it's going to be Q over 24 times epsilon naught. Okay, so that means that our answer should just be 1 over 24, right? So let's see if we get 1 over 24. Let's just check that with, I can't do that in my head. Okay, so let's just print 1 over 24 down here. Print 1, you can't even see it. 1 divided by 24, and I get the same thing. You can't see that. Right there. Same thing. That was a trick. Okay. If you don't like tricks, I completely understand. I don't like tricky problems. I do like setting, if you set that up, if this was a test and you set it up the way I did it, and then you got stuck and like, I can't do this integral, I'd probably give you full credit if you showed all your work. That's just me on my test, but you may have a different person teaching your class, and you probably do, unless you're one of my few students. Okay, talk to you later.